Ocean currents play an important role in regulating Earth's climate. They transport warm and cold water around the globe. These currents are driven by the density and the salinity of the water. That's why being able to monitor the ocean salinity is crucial to the better understanding of ocean currents. Soil moisture is another important factor influencing the climate, because there's a direct link between soil moisture and the humidity of the atmosphere. Having a better knowledge of global soil moisture will contribute to understanding the Earth's water cycle. To precisely measure these variables will be the task of one of ESA's Earth explorers, SMOS, which stands for Soil Moisture and Ocean Salinity, and which will investigate the source of all life on Earth, water.
The importance of the SMOS mission is, in the first place, that we are supporting science. That means we are furthering the understanding of how our world is working, how our climate is working, and how it is changing, either naturally or by the impact of man. Eventually, we hope that by demonstrating the possibility of doing these measurements, that it will become an operational mission which is used by weather services, disaster monitoring agencies, and so on.
To improve our understanding of the water cycle and advance weather and climate predictions, SMOS will measure soil moisture and ocean salinity. To achieve the required accuracy for observing both the amount of salt in the oceans as well as the amount of water in the soil, it would take an antenna with a 20-meter diameter. An antenna that big would be almost impossible to put into orbit. That's why SMOS will deploy an instrument never seen before in space. 3 arms covered with a total of 69 small antennae that make a 2-dimensional interferometric radiometer. Together, these 69 small antennae act like one big antenna. It took 10 years of research and development to complete this new radiometer. The satellite doesn't actually look for salt. It receives the radiation of the oceans and then looks for the electric characteristics. Because the conductivity of the water is influenced by the salinity, the satellite is able to measure the amount of salt. The SMOS satellite is so accurate that it'll be able to detect 0.1 grams of salt in a liter of seawater from space.
The satellite goal in terms of measuring soil moisture is to get access to a global coverage of the humidity in the first centimeters of the soil all over the globe, every 3 days maximum, with an accuracy of about 4%, which is a very small amount of water.
With the SMOS satellite, scientists will finally be able to work with accurate data on the Earth's water cycle. This continuous exchange of water between the oceans, the atmosphere and the land is one of the most important processes controlling the Earth's climate. Still, it is relatively poorly understood. Until now, data on the 2 variables, soil moisture and ocean salinity, has been sparse and often incomplete.
The SMOS mission actually directly corresponds to the current lack of global measurements of those 2 variables. In addition to that, we also have an objective to provide data for cryospheric sciences. That's a secondary objective in the mission design. However, we strive to correspond to that one too.
Demonstrating the new radiometer and collecting data that will allow better weather and extreme event forecasting. That's what the SMOS satellite will do once launched, getting a closer view on water by looking from space.